Hey everyone, and welcome. When you think about railways, you probably picture these massive locomotives hauling tons of freight, or maybe those sleek passenger trains zipping across the country. They're industrial marvels, for sure. But have you ever really stopped to think about how these colossal systems are actually built? Well, today, we're going to do just that. We're diving deep, from the molten heart of a steel furnace all the way to the absolute cutting edge of physics to find out. This quote right here, it nails it. This isn't just about bending huge pieces of metal. It's a symphony of incredible power, microscopic precision, and just sheer human creativity, all working together on a scale that's kind of hard to wrap your head around. So where does it all begin? Whether it's a 1,000-car freight train crawling through the mountains or a bullet train blurring past the countryside, it all starts with one thing: a single, humble piece of steel rail. So let's start there, right at the very beginning. Now, before we get into the how, we really have to talk about the why. Because railways aren't just a neat way to get from point A to point B. No, they are the circulatory system of our entire global economy. Just look at this number, $700 billion. That's how much stuff gets moved by rail every single year, and that's just in the United States. It gives you a real sense of the incredible economic weight that is literally riding on these steel tracks every single day. And I love this metaphor because it's so true. Every track is like an artery, pumping the lifeblood of commerce, raw materials, finished goods, you name it, into the heart of our cities and industries. And the foundation for all of it? Well, it's a very, very special kind of steel. Yeah, this is not your average, everyday steel. High manganese steel has this incredible property called work hardening. Get this, the more stress you put on it, the harder its surface becomes. It's like the more you beat it up, the tougher it gets. It's why a single track can handle heavier and heavier trains for decades, saving billions in replacement costs. It's pretty amazing stuff. All right, so how do you actually make this super steel and then shape it into a perfectly formed rail? Well, it's a process of fire, water, and just incredible force. Okay, let's break this down because this is like a high-tech ballet. First, you pre-treat the molten iron to get rid of all the nasty stuff. Then, after refining it, it goes through this crucial step: vacuum degassing. They literally put the molten steel in a vacuum to suck out gases like hydrogen that could create tiny, invisible weaknesses. Only after it's been purified is it cast, rolled, and finally heat-treated. Every single step is controlled down to the smallest detail. It's way more advanced than just pouring metal into a mold. I mean, just try to imagine this. We are talking about temperatures hot enough to turn solid rock into a glowing, liquid river of steel. This is where those critical alloys, like manganese, are added with absolute precision to get the chemistry just right. And check this out. This is where you see that mix of raw power and the need for absolute purity. After the steel is cast into this big rectangular block called a bloom, these ridiculously powerful water jets, we're talking over 3,700 psi, literally blast away any steel or impurities from the surface. This makes sure the final rail is flawless before it gets squeezed into that iconic I shape by a series of massive rollers. Okay, so we've got the path. Now, what about the machine that rides on it? Assembling a modern locomotive is an engineering feat that's every bit as complex and precise as forging the rails themselves. And it all starts right here, with these massive, and I mean massive, coils of raw steel. These things weigh tons, and they're the raw material that will eventually become the frame, the walls, the very skeleton of the locomotive. And this is where you see that incredible combination of technology. On one hand, you have CNC lasers slicing through thick steel with a beam of light for pinpoint accuracy. And on the other, you have hydraulic presses that use thousands of tons of raw force to bend that steel into the complex shapes needed for the body. So all those perfectly cut and shaped pieces are brought together, and then automated welding robots get to work. They glide along pre-programmed paths, creating thousands of perfect seams that fuse all those individual parts into one immensely strong structure. But a locomotive is so much more than just a big steel box, right? It's basically a mobile power plant. The foundation is the underframe. It supports everything. The bogies, those are the wheel assemblies, are balanced to within thousandths of an inch. But the powerhouse is the really cool part. That huge diesel engine, it doesn't actually turn the wheels directly. Nope. It powers a giant generator, which creates electricity to drive the motors. It's all about maximum torque and efficiency. And overseeing it all is the brain, a computer that's monitoring thousands of signals at once. So you've got this perfectly forged rail, and you've got this powerhouse of a locomotive. But a whole railway track? Well, it's only as strong as its weakest link. And that's the point where two rails meet. And this really shows that not all welds are created equal. In the factory, you can use flash contact welding. They pass a massive electrical current through the rails to forge them together, creating a joint that's literally as strong as the rail itself. But out in the field, in the middle of nowhere, you need something portable, like gas pressure or thermite welding. They get the job done, but yeah, there's definitely a trade-off in quality. And this is a trend we're seeing across the entire industry, from making the locomotives to welding the track. Automation is changing everything. I mean, robots can work 24/7, they don't get tired, they can perform these incredibly complex tasks with a consistency and precision that a human just can't match. And sure, the initial investment is huge, but over the long run, the gains in speed and quality are just undeniable. For over 200 years, trains have worked on a really simple principle: a steel wheel rolling on a steel rail. It's simple, it's effective. But what if the future of rail travel has no wheels at all? So welcome to the world of maglev, magnetic levitation, and it is some seriously cool science fiction level stuff. The concept is kind of mind-bending. You use one set of powerful electromagnets to literally lift the entire train up off the guideway, just floating it there. Then another set of magnets creates a propulsive wave that pushes and pulls the train forward. With no wheels and no friction, it's less like a train and more like a plane flying just a few inches off the ground. So what happens when you get rid of friction? Well, you pretty much get rid of the speed limit. China's new CRC 600 maglev is designed to cruise at 600 kilometers per hour. That's about 370 miles an hour. This isn't just about being a little faster. This is technology that completely closes the gap between high-speed rail and commercial airplanes. And right now, there's this fascinating race going on. Japan's SC maglev holds the world speed record, but it uses incredibly complex, super-cooled magnets. China, on the other hand, is using a slightly less complex system. Their strategy is more focused on making maglev a practical, widespread option for mass transit. So it's this clash of philosophies. Japan is building the technological showcase, the Formula One car, while China is trying to build the reliable daily driver for everyone. Ultimately, this isn't just an upgrade. This is a complete reimagining of what a railway can be. It's a fundamental shift, moving away from the brute, mechanical force of engines and wheels to the elegant, silent, and unbelievably fast world of controlled magnetic fields. From molten steel to levitating magnets, the journey of the railway has been one of constant, incredible innovation. And as we stand on the edge of this new magnetic era, it leaves us with a pretty fascinating question to think about. Thanks for joining me on this one.